Hello, my name is Deryc Painter. I'm a researcher at the Global Biosocial Complexity Initiative at Arizona State University. Today I'm going to be talking about a methodology that I developed to find innovations and in a knowledge landscape, most specifically of evolutionary medicine as our test case. So let's go ahead and get started so I can try and stay under time. What do we think we know about innovations, right? So we know a lot about innovations, or we think we do at least, because it's not something new. The idea of understanding innovations and facilitating innovations has been around for a really long time. And so what I want to do is I want to offer some evidence, and then I'm going to make a couple claims before we dive into the nuts and bolts of the experiment, right? So let's start with combinatorial evolution, right? The idea behind combinatorial evolution is that the majority of innovations and new ideas do not come as some lightning bolt strike out in the woods, de novo ideas. They're actually bits and pieces of ideas that already exist combined in new and interesting ways, right? So we see that in things like the genome. We also see that in patents, and there's been a lot of work that's figured this out, right? So here's the main one I want to talk about: invention as a combinatorial process, right? So Haitian, Deborah, Luis, and Jose all got together and used their patent database and found that the most successful patents are not using brand new citations or even uncommon citations. What they're actually doing, these successful patents are taking very common, often cited work and combining it in new ways, right? And so that's been shown in their follow-up publication with Strumsky and Lobo. It's been shown here with and technological origins, right? So all these all come to the same conclusion, that the most successful patents are combinations of things that already exist, right? So the idea of recombination is important for innovation, not just invention, right? So that's kind of what we get with the patents, but it's important for innovation, right? So this group, then this, like I said, it goes all the way back before Schumpeter, but I just wanted to highlight Schumpeter here because I'm going to be talking about him a little bit later. This is 1939 book, Business Cycles. Came up with a lot of really interesting ideas that are still talked about today. Here's one of them from 98, talking about resource recombinations for a Schumpeterian evolution, right? So here we have Lee Fleming talking about innovation as a search criteria in a knowledge landscape. And there's recombination in that search pattern. So, I mean, there's lots of these things, right? I don't have time to go into every single one of them. I just wanted to make the point that this is a well understood and accepted, idea. Now, innovation is also linked to interdisciplinarity, right? So we have a lot of publications that show this. So, I mean, yeah, it just keeps going, right? So the idea is that interdisciplinarity increases innovation up to a certain point, right? So there's a trade-off, right? You get some diminishing returns past a certain amount of interdisciplinarity, right? And so if you get on some Zoom meetings, sometimes at work, you get a little too much interdisciplinarity going on, it can hinder instead of help. So those are just the claims, right? I mean, they're pretty basic stuff. Nothing I'm not pulling any crazy ideas here. So claim one is that most innovations come from novel recombination of existing ideas, right? And I offered some publications that have found this to be true. And then claim two is innovation is linked to interdisciplinarity, right? There's some sort of relationship there between facilitating innovations and how interdisciplinary the research or the group is. So made those claims. Now let's talk about classifying innovations for a second. If you're going to classify innovations, it's not an easy thing to do, right? Because the classification has to be specific enough to identify the innovation amongst all the other stuff. And it also has to be broad enough so that you can account for ideas you've never thought of, right? Like, the definition of innovation for some people. Now, here we go. Let's talk more about Joseph Schumpeter, right? So he wrote this book, Business Cycle, and he came up with this invention, innovation, and imitation framework. And this is still used today, right? So these three things, right, it comes out to invention, which is creating something new, right? And then innovation is creating an impact, right? So it has to be useful. Not only does it have to be new, but it has to be useful. And then imitation is the adoption by others, right? So these are pretty basic steps that most people find to be reasonable when talking about things like innovation. Now, for my study, we have a huge corpus of evolutionary medicine publications, right? And way more publications than I could ever read in, the span of my dissertation when I was doing this research. So there had to be a better way, right? So using computational linguistics tools, we're able to extract keywords, and I created this novelty and persistence framework, right? So novelty directly relates to the invention. Innovation and imitation now have been grouped together into one idea called persistence. Now, this is the idea that if you have a publication, right, you have all these publications in your corpus, you've extracted all these keywords for each publication, and when you start comparing those keywords by year, by paper, you can find publications that bring new keywords that have never been seen before, right? You have to have a baseline of keywords, but once you have that, you can start saying, oh, this is a new keyword, right? And then so we take it a step further, that you don't just introduce new keywords, but those keywords have to stick around for a while, right? So novelty and persistence. And this is how we identified innovations using the metadata from these publications, right? So here's a little flow chart, right? We start with the evolutionary medicine corpus, right? So people who self-identify in evolutionary medicine, along with the two most prominent textbooks at the time, all the authors and contributors from that. Then we take those people, we get all of their Web of Science publications, find the PDFs, turn those PDFs into text, then we create the word frequencies, we compare those keywords to a reference corpus. In this case, it was the Baker-Brown corpus of American English 06. This gives us keyword counts by year. We can then take those keyword counts, right, and find those novel persistent keywords and then the publications that are attached to them. And the nice part about this is we can then rank the publications based on how many new keywords they introduced and how many stuck around, right? So this gives us a list of the top 100 most innovative publications in evolutionary medicine. So that's all well and good, right? It's easy to hand wave and say, oh, we think this novelty and persistence idea is a good way to identify innovations, but how do we know that we're even on the right track? So what we did was we found first that the total corpus, all evolutionary medicine publications, average about 6.4 citations per year. Now, the innovative publications that we identified average 17.2 citations per year. this plot here might be a little difficult to read at first, but we have it on the x-axis is citations per year, then the cumulative probability of how many, the odds of having that many citations per year. Then we did a 2-sample KS test and found a KS statistic of 0.23 and some fairly good significance, 10 to the minus 4. And what this KS does is it basically compares two distributions, right? They don't have to be normally distributed because it's non-parametric. So what we see here, right, is there's the blue line, that's all papers. And you can see there's the confidence interval there shaded lightly. And then the orange, way more citations, a huge difference between the innovative publications and all publications. So now that we have a way to identify innovative publications, right? And then we identify these publications, then we take them to, I actually had Randy Nesse look at some of these and confirm that yes, they were interesting and useful and possibly innovations. So once we have innovations now, we can map where they are in the network if we can figure out how to classify different areas of the network. So we build a bibliographic coupling network, right? So this is, we have all these publications. We have publication A, we have publication B here. They both cite publication C, so therefore we just draw a line between them. And we do this for the whole corpus, right? And we use weighted, where the weight of the edge is proportional to the number of citations. We also did just a binary, connected or not. We found that publications remain the same, or the results didn't change at all. So evolutionary medicine exhibits what's called a rich club structure. Now what we have here is a bibliographic coupling degree threshold, right? And a rich club coefficient. So basically, the rich club coefficient is defined as the ratio of the number of edges among nodes with a degree larger than a certain number, that's the bibliographic coupling threshold at the bottom, to the number of maximally random ensembles that share the same degree distribution. So basically, we make a bunch of random graphs and we compare how many nodes, and we smooth that threshold all the way down. And as the rich club coefficient peaks, we can say, boom, there is the optimal rich club. It sits about 427, I believe. So 427 connections in order to be considered part of the rich club. Now this is kind of hard to visualize in your head, so I took a sample from 2007, because the actual full thing you wouldn't be able to read. It's all a giant hairball for most part. But if we look at 2007 for an example, I've identified where the core, one of the core areas in the network is, and where one of the periphery areas of the network is, right? So these are kind of intuitive once you hear them, but sometimes it's nice to get a nice visualization to kind of drive home that point. Now the big finding is that innovations are disproportionately likely in the periphery of the network, right? So this graph here, we have bibliographic degree at the year of publication, cumulative probabilities for how many of those publications are in the periphery and their citation and their bibliographic coupling degree, right? So how they're connected, how many connections they have to other papers. And what we see is that in the periphery, the innovative papers are overrepresented, right? So in the periphery, 40% of the innovative papers have a bibliographic coupling of less than 2, while only 20% of the papers overall are this low. And then as the curve of these two curves overlap towards the core, this shows that the number of well-connected innovative papers is the same as expected by chance, right? So an overrepresentation of innovations in the periphery of the network. So let's summarize this really quick. Papers that produce novel, persistent keywords typically receive more citations per year than average, suggesting that they are more innovative. The evolutionary medicine knowledge landscape is organized as a rich club, and the innovative publications are overrepresented outside the rich club structure in the periphery of the network. So that summarizes the findings. Let's talk about the big conclusion here before I run out of time. While maintaining a thriving core may be crucial for developing existing ideas, allowing for a diverse periphery could be equally important to avoid stasis and promote necessary adaptation. It is likely, as previous work in bibliographic coupling networks suggests, the paradigm exemplified by a scientific field is, in a sense, defined by the stability of the rich club, and we are more likely to encounter a Kuhn-like scientific revolution originating in the more volatile interdisciplinary periphery, right? So remember, these new novel keywords that persist typically aren't the first time these keywords have ever been seen in all of science. It's the first time they've been seen in evolutionary medicine, and that is in fact the innovation, right? Bringing that across disciplinary boundaries, and that occurs in that loosely connected interdisciplinary periphery. I want to really quick acknowledge my co-authors, Manfred and Bryan. They are wonderful researchers, and if you get a chance to work with either of them, I would suggest you take it. And that pretty much wraps up my talk. I think it's a couple minutes over, but thank you. And I look forward to answering any questions you might have.